Hey students, in this video we're going to cover logarithmic equations. Our objectives are to solve logarithmic equations and to review Euler's number and the natural and common logarithm. So when we're solving a logarithmic equation, two things can happen. We either have logarithms on both sides or we have a logarithm on only one side. In the case of having a logarithm on both sides, what we want to do is condense both sides of the logarithm. So in this example, this would be the same as having log base 3x equals, and remember where we subtract two logarithms, we can divide the inputs. So that would be log base 3 of x plus 3 divided by 4. And so if the logarithms of two things are equal, the two things themselves must be equal. So because these two logs equal, the implication is that x equals x plus 3 divided by 4, since those two logs are equal. In the case where we have only one logarithm on the side, we want to make an exponential equation. And remember, you have a base, you have an exponent, and you have the power. So we're going to say that could be rewritten as 3 to the 4th equals x, and then solve that equation. Now that's easy, x equals 81, but that's what we're going to be doing in this section. So our first example is log base 4, 3x minus 1 equals log base 4, 4 minus x. In this case, we have a log on each side, but they're already condensed, meaning we have one log on each side. So since these two logarithms are equal, then 3x minus 1 is going to just equal 4 minus x. We can just ignore the logarithms because the inputs have to be equal. So next, to solve for x, we're just going to add x. We do plus x here, excuse me. So we would get 4x minus 1 equals 4. And so then 4x equals 5 and x equals 5/4. When it comes to logarithms, you have to be able to take the solution and replace it in the original function. And these inputs of 3x minus 1 and 4 minus x have to both be positive for that solution. So 5/4 is 1.25. And so if you were to take 1.25 and substitute it in here and substitute it in here, you would get positive numbers for both of those. So that's how we know. Now, another way to do this is just this needs to be greater than 0 and that needs to be greater than 0. So 3x minus 1 is greater than 0, which means that x needs to be greater than 1/3, and 4 minus x is greater than 0 means that x needs to be less than positive 4. So we're looking for a value of x that satisfies both of those, so greater than 1/3 and less than 4. So we're really looking at a value of x between 1/3 and 4, and 1.25 fits that, so that solution actually works. For example 2, we have log base 2x cubed and log base 2x. So again, we already have this condensed, so we would get x cubed equals x, and then x cubed minus x is going to equal 0. We can factor out an x to give us x times x squared minus 1 equals 0. And we can further factor to get x times x plus 1 times x minus 1 equals 0. So you get x equals 0, x equals -1, and x equals +1. So again, you have to go back and check your solutions. Again, the inputs have to be positive. They can't be 0 or negative. So x equals 0 won't work because you would have 0 in both of the x's. X equals -1 won't work because you would get -1 for the x's if you substitute them in. So the only real solution is x equals 1, because that would give you log base 2, 1. And again, the reason we can't have negatives is if you have something like log base 2, we'll say negative 4 equals, and we'll say this is x, for instance. So then the corresponding exponential equation would be 2 to the x equals negative 4. And because 2 is a positive number, you can't raise a positive number to any exponent and get a negative value. And that is why these numbers must be positive. That doesn't mean your x can't be negative. It just means that once you substitute it in and evaluate, the input has to evaluate to be a positive value. So again, in this case, only x equals 1 would work. For example 3, we have 2 log base 7 x equals log base 7 2 plus log base 7 x plus 2. So first we want to condense, which means we're going to make all our constants. We're going to turn those into exponents. So we would get log base 7 x squared equals, now we are adding two logarithms, which means that we multiply. So we're going to get log base 7 of 2 times x plus 12. And now we have condensed our logarithms to 1 on each side, so we can drop the logarithms. So we get x squared equals 2 times x plus 12, which is just 2x plus 24. We subtract x squared from both sides. We're going to subtract 2x and 24 from both sides. So we would get x squared minus 2x minus 24 equals 0. And so then you would get x minus 6 times x plus 4 equals 0. And you would get x equals 6 and x equals negative 4. So the value of negative 4 is going to present a problem because it would make this x negative. So you exclude that. But the value of 6 works because 6 would make a positive here and 6 plus 12 is positive. So the only solution is x equals 6. For example 4, we have log base 125. You can read the rest. All right, so now in this case, we're going to end up with a logarithm just on the left. So we're going to get log base 125. And since we are subtracting two logarithms, that means we divide these inputs. So that's going to be 3x minus 2 divided by 2x plus 3 equals 1/3. And again, when we have a single logarithm, you want to make an exponential equation. So that's going to be 125 to the 1/3 power equals 3x minus 2 divided by 2x plus 3. And 125 to the 1/3 is 5. So we get 5 equals 3x minus 2 divided by 2x plus 3. Our next step would be to multiply this denominator of 2x plus 3 times 5. So we'll just do that up here. So we're going to get 10x plus 15 equals 3x minus 2. And we subtract 3x from both sides. So we get 7x plus 15 equals negative 2. We subtract 15 from both sides, so we would get 7x equals negative 17. And then we divide both sides by 7. And so x is going to equal negative 17 divided by 7. And again, that value is it's like negative 2.43 or something. So when we take the negative 2.43 and substitute it in over here, you're going to have 3 times a negative 2 something. And then when you subtract 2, that's going to be negative. So the logarithm can't have a negative input value. So in this case, we're going to get no solution because the negative 2.43 doesn't actually work. Our only possible solution does not work. And again, if it makes just one of the logarithms have a negative input value, the problem can't be solved. All right, so this should be example 5, not 6. So example 5. We have 3 log x squared minus 21x minus 6 equals 0. So first we're going to add 6. Let's just say that equals 6, and then we won't have to take a step. So we just added 6 to the other side to get equals 6. Next, we divide by 3, and we would get log x squared minus 21x equals 2. And remember, if you have a logarithm and you don't have a base, the base is assumed to be a 10. This is what we call a common logarithm. A common logarithm, you don't see the base. That means the base is 10. So the exponential equation that we make is 10 squared equals x squared minus 21x. And so that's going to mean 0 equals x squared minus 21x minus 100. And that's going to be x minus 25 and x plus 4. So x equals 25 and x equals negative 4. So in the case of 25 will check out 25 squared minus 21 times 25 is going to be positive. And then in the case of negative 4, negative 4 squared plus 84 is also going to be positive. So both of our solutions actually work. All right, so moving forward, we're going to be using the natural logarithm. The natural logarithm is a logarithm that has a base of e, and it is used so often in math that it has its own designation, which is the ln of x. So anytime you have a logarithm, anytime you see ln, it means the base on that logarithm is always e. And you should remember from Algebra 2 that e is called Euler's number, which is 2.71828. And these two properties of logarithms are going to be helpful sometimes. E to the ln of x is just x, and the ln of e to a power is just the ln of e to an exponent is just that exponent. And the same three properties of logarithms apply to the ln. And what that means is if you have like the ln of, we'll say, two functions, f times g, that's going to be the ln of f plus the ln of g. If you have the ln of two functions that are being divided, that's going to be the ln of f minus the ln of g, as long as that g function is not 0. And then the ln of a function raised to a power is going to mean you take that exponent and move it to the front and multiply by that logarithm. So those same three properties apply to the ln. So our next example, we have 3 ln x minus 2 equals 1 minus ln x. So we want to isolate the logarithm. So that would give us 3 ln x. We add 2. That's going to equal 3 minus the ln of x. And we can add the ln to the other side. So we're going to get 4 ln x equals 3. Divide both sides by 4. We get ln x equals 3/4. And that's going to mean we can make an exponential because we have a single log. Remember, for ln, the base is e. So we're going to get e to the 3/4 equals x. Let me jump to the calculator. Calc. So we did e to the 3/4. So e to the 0.75 is 2.117. All right, so 2.117 equals x. I'll leave it to you to go and check that. But clearly it makes those logarithms positive, so that is not a problem. Example 8, we have the ln of x equals 3. So first, we're going to make an exponential equation using this outer logarithm. And since that logarithm has a base of e, we're going to get e to the third power equals the natural logarithm of x. And to solve for x, we're going to make another exponential equation where we're going to get e to the e cubed, because this base is e. So e to the e cubed equals x. And that's basically e to the like 9th power or something like that, which is a gigantic number. I'll show you that if you want to see it. So e to the e cubed. So it's at 528,491,311.5. So yeah. So we'll just say that is 5.3 million equals x. All right. So that concludes this video for solving logarithmic equations. In the next video, we're going to talk about solving exponential equations using logarithms.